Hello. I would like to explain the theoretical background of the Nobel Prize in Physics, Physics Nobel Prize 2022, awarded to Aspect, Closer, and Zeilinger for their work on entanglement. Essentially, they showed or confirmed the predictions of quantum mechanics, which is outstanding. It's brilliant. So this video is not about the experiment, but actually about the theoretical background. And the beginning of the story is by EPR. EPR stands for Einstein, Podolsky, and Rosen. So this is a paper from 1935, an old paper, in which EPR wondered whether quantum mechanics describes reality or some sort of a statistical approximation. And let me, instead of discussing philosophy, just go straight to the gedanken experiment that EPR proposed. I will present not exactly the original paper, but a version by Aronov and Bohm with two spins. So spin, as we know, is some sort of internal rotation of a particle. And let's assume that we have two electrons. We measure the total spin of the two electrons. So we have two electrons. And we measure the total spin of this system without measuring the individual spin. And since each one of them has spin half, the total spin of the two electrons can be either 0 and 1. If the result is 1, we throw away the system. We're not interested. We restrict ourselves to the cases where the total spin is 0. That's called also the singlet. Now, quantum mechanics tells us that the state with a singlet is a state where the first spin is up and the second is down, minus the second is down, and the first is up. So quantum mechanics doesn't tell us what is the spin of each individual particle. It just tells us that when the total spin of the two electrons is 0, we are in a superposition or in a linear combination where one spin is up and the second is down, together with one spin down and the second is up. And somehow quantum mechanics tells us that actually the spin of each individual particle is not well defined at this stage. It's in a superposition. So let's see what is the implication of that. What EPR, Einstein, Podolsky, and Rosen propose is to do the following. Let's move apart the two electrons. So suppose that they are far, far away in distant galaxies. And suppose that we measure the spin in the z direction. If the result, if this spin, the first one, points up, then the other is down. If the result of the first spin is down, then the result for the second electron is up. So on one sense, or in some sense, it makes sense. I mean, the total spin is zero, so what else can it be? But wait, if before the measurement, the spin of this particle, let's say the left, was not well defined, how come the other particle, which might be a light year away, knows to point in the other direction, in the opposite direction? So EPR said there is some spooky action at the distance. Somehow they communicate. But that's impossible. They cannot really communicate because this distance may be light year, and we can do the experiment. We can do the two measurements of the two particles in a time interval, which is, let's say, 1 second. And so they don't have time to communicate. They cannot communicate in a speed faster than the speed of light. Now, alternatively, we can decide that we measure the spin along the, let's say, x direction, and then if the first particle points to the left, the other should to the right. So we can even choose randomly in which direction to measure the first spin, choose randomly which direction we measure for the other particle, the other spin. And in the case that we happen to measure both in the x direction, we will find always that they point in the other direction, in opposite directions. So somehow EPR said they communicate in such a way that they will always be in opposite directions. But then EPR said, but wait, this is impossible. And this is impossible because, again, they cannot talk to each other. So EPR concluded the following. Logically, according to EPR, the only possibility is that actually the spin of the two electrons was well defined even before we measured it. So this description of quantum mechanics, where the spin is not well defined, that for each one of them it's either up or down or actually both, that doesn't make sense according to EPR. It's okay, kind of statistically. Quantum mechanics provides us what will happen statistically when we make many measurements, but for each experiment, for an individual experiment, it does not reveal the reality, but some sort of approximation that works when we carry out many measurements. So what they say is that, moreover, is that if we somehow knew more about the particle, we could determine the spin of each one of them. The reason that quantum mechanics gives us a statistical answer is that we are missing some information about each one of the particles, and had we known that information, what people call hidden variables, we could determine, or we could know the spin of each one of the electrons, because according to EPR, it doesn't make sense otherwise. So that was the conclusion of EPR. And 30 years later, John Stuart Bell came with a brilliant idea, a variation of the EPR experiment. So what he said is the following. In EPR, we measure, let's say, the spin along the z direction, and suppose that we have the following results for some measurements. So that's the first spin, and we'll write below the results for the second spin. So in the singlet state, let's suppose that the first spin is up, up, down, up, down, up, down, down. And let's suppose that then the second spin has to be down, down, up, down, up, down, up, up. So what Bell said is the following. Suppose that the spins of the two particles actually exist in reality. It's just us, we don't know. But suppose that this is the setup, and then when we measure the spins of the two particles, that's what we get. Now suppose we repeat the same experiment, but with a tiny variation. For the first spin, the measurement is along the z direction. For the second spin, let's measure along z prime, which is tilted by theta. Let me write it more clearly. So we tilt the direction of measurement by a small angle theta. Then let's see what will happen. For the first spin, we'll get the same results because it's the same experiment. So if we take 8 measurements, we'll have the same results. For the second spin, if we repeat the same experiment, but with a tilted direction, z prime, so not exactly the same, it could be that sometimes we'll get a flipped spin. The reason is that z prime is not z. We measure in a different direction. So with respect to z prime, which is close to z but not the same, the result of the spin with respect to z prime, the second spin, can be actually down. And then there is a chance that we will measure down, down, or maybe up, up, like in this case. So there is a tiny probability, let's call it P of theta, for either up, up, or down, down. Of course, for theta equals 0, the probability for that is 0 because we started with a singlet. Okay. Now Bell says, let's increase the angle times 2. So instead of theta, let's consider 2 theta. And that can be carried out by tilting the first axis by theta as well, but to the other direction. So let's call it Z double prime for the first spin. And again, Z prime, which is theta, for the second spin. So then what can happen? Now, the first spin can flip. So roughly, let's suppose that this spin flips. So roughly, P of theta, of 2 theta, sorry, is roughly P of theta. That's, or 2 times, sorry, P of theta. That's what we expect. Because now the chance of, when we carry out these measurements, that to have spins up, up, or down, down should be roughly 2 times. But is it more than 2 times or less than 2 times P of theta? What happens when we increase theta by a factor of 2 or make the relative angle 2 theta instead of theta? So in this example, we have 2 cases with spins pointing in the same direction instead of 1 as in the first case. However, we can imagine something else. So let's consider the first example. And this time, another thing that can happen is that because we measure with respect to Z prime, that this spin will flip, that we'll measure up instead of down for exactly the same spin that was also flipped for the second electron. So now, in this example, we see that it's like the first case, just it happened, there is a small chance for that. That means that according to just logic, that P of 2 theta is less than 2 times P of theta, because there is a small chance that there will be some sort of like double error that, but we will not notice double error. It will look like spins are pointing in opposite directions. So to conclude, if we assume that we have singlets and we measure in relative angle theta, there is of P of theta for these 2 possibilities. However, P of t theta, we expect it to be less than 2 times P of theta, because when we measure with respect to tilted axis, sometimes the 2 spins flip with respect to the measurement along the z direction, and that case causes p of t theta to be less than 2 times p of theta. So this is the case where, if we compare the original to the last, we see this case that causes us to believe that p of 2 theta is less than 2 p of theta. And the assumption behind this plausible answer is that from the beginning, as Einstein, Podolsky, and Rosen conjectured, the spins, the positions of the spins are well defined. Now let's see what quantum mechanics tells us. If we do the calculation, quantum mechanics tells us that p of theta is sine square theta over 2. I didn't present the calculation, but that's the result. Therefore, p of 2 theta is 2 times sine squared theta 2 times cosine squared theta over 2. And this number is larger than 1. Therefore, p of 2 theta is larger than 2 times p of theta, which is amazing. Quantum mechanics predicts that p of 2 theta is larger than 2 times of p of theta, and that the conclusion must be that before the measurement, actually, the individual spins were not well defined. It's not that they are well defined and we don't know them. They are really not well defined before the measurement. This picture that we have a set of spins, some kind of classical variables that we simply don't know what they are before the measurement, but there is some well-defined direction as EPR conjectured, that leads to this conclusion. However, quantum mechanics predicts something else. What aspect Clauser and Zeilinger did, they measured. They said, okay, let's go to the lab. Let's carry out this experiment and let's see whether EPR were right or quantum mechanics is right. And the answer is that quantum mechanics is right. This inequality p of 2 theta larger than 2 of p theta was confirmed in the experiments of Aspect, Clauser, and Zeilinger. And for that, they were awarded the Nobel Prize. That means that what Einstein thought, that Einstein said, well, God does not play dice, because he didn't believe that there is kind of statistical nature. It says God does not play dice. It's just that we don't know the reality. And if we knew the hidden variables, we could predict what's going on. And quantum mechanics and the experiment tells us, no, God plays dice. The spins themselves, the position, do not, the direction does not exist before the measurement. The two spins are in such a superposition. And their spin is not really well defined before the measurement. The description of quantum mechanics, this description is confirmed this is the reality. It's not that we don't know the direction of the spins. It's really that it is not well defined before the measurement. That's the deep meaning of this inequality, which is called Bell inequality. And that was confirmed in the experiment. And for that, the three gentlemen were awarded the Nobel Prize in Physics 2022.